Have to look at me. So we are moving into a new unit, and this unit is going to be on, doesn't work with the eraser, on exponents. I don't know why all of a sudden it is writing tiny. Let's see what we got here. Oh, because we're at 56%. Let's clear that. We want it to be pretty. We want that at 100%. So what we're doing is I'm off to a bad start. Exponents and logarithms. But today we are focusing on graphing logarithms. I don't know what furniture Miss Walters has to move next door. Again, she's been moving furniture like every single day, but it makes my whole room shake. So, like I said, a little distraction there. I'm a little ADHD today. Graphing, I'm a little ADHD every day, but oh my God, can you hear that? It's like an earthquake. And we've dealt with exponents in the past, right? Exponents are anything raised to a power. So we could have x squared as an exponent, right? In which case 2 is our exponent. X to the 4th, 4 would be our exponent. X to the -6, right? We can raise something to any power. Up to this point, though, our variable has never been the exponent, right? It's always been the thing that we're raising it to. So what we're starting on now is dealing with the exponent as the variable. We don't know what it is. It's our input value. It can be anything we want it to be. And so we're going to start working on how to solve those problems. But for today, we're really just talking about graphing exponential functions. And so we're going to start with some vocabulary, and then I'm going to do like one sample problem, and I'm going to let you guys just kind of absorb that. And then when I see you on Thursday, we'll move more into transformations and we'll put it all together and then have an assignment with it. So for the vocabulary, what we're talking about is, we'll start with the exponential parent function. That means it's the one where we start. It's the one that everything is kind of based on, right? And the exponential parent function is f of x, right? Which is just the name of the function. Oftentimes we call it y, right? It's our output. Equals b to the x. B is just a number. X is just a number, right? This is our base raised to a power, right? What we're saying, though, is that our variable is the exponent itself when we're dealing with exponential functions. So some things that you want to know. If b is greater than 1, this is a function of growth, right? It represents exponential growth, which means that the function is increasing, right? So if this right here, this b is greater than 1, it's always going up. It's increasing, right? If b is less than 1, which means it's either negative or a fraction, right? Fraction can be less than 1, right? 3/4 is less than 1, but it's not negative. If b is less than 1, it is an exponential decay function, which means that it is getting much smaller. So it's exponential decay, which means that it is decreasing. Decreasing. So think about things where it would be growing, right? If compound interest, right, grows something exponentially. It moves at an exponential rate. Where we use decay, the reason we call it decay more often than not is because it's how we determine how old an element is. The way we can date fossils is by the exponential decay. We know the half-life of an element, and as carbon breaks down inside, say, a bone or whatever, we know how old it is based on the half-life of carbon, that decreasing at an exponential rate. So this one is getting increasing at an exponential rate. And when we say exponential, it's huge. Think about how things grow exponentially. If I have 2 to the second power, that's 4. If I have 2 to the third power, that's 8. If I have 2 to the fourth power, it's 16, then 32, then 64, right? These things get huge really, really fast when we're talking about exponents, but they can also get small really, really fast when we're talking about exponents, right? And so those are some of the things that I want you to keep in mind. Another thing that you're going to have to understand is anytime we're dealing with exponents, we have something called an asymptote. Asymptote. All an asymptote is a line which the graph, a line that the graph of a function can get close to but never touch or cross, right? It can get infinitely close, infinitely close to, but never touch or cross. All right. We'll get some examples of that going on. A couple other things you're going to have to know. We've discussed these before, but you probably need a little reminder of domain and range. Does anyone remember what the domain and range are for like 500 million imaginary points? Can anyone remember the domain and range, or even anything that they have to do with? I'm not even seeing a nope in the chat box or a yep. For anything, what would the definition of domain or range be? No, but that's a good guess, Alfonso. You are allowed to not know. I will not hold it against you. The domain is the set of all possible inputs or x's, right? And if the domain is the set of all possible inputs or x's, what do you suppose the range would be? It's okay, Bailey, you do not have to apologize for that. The range would be the set of all possible outputs. Outputs, or y's, right? So these are the basics of what we're going to be dealing with today, right? what's going to happen is you're going to get problems, and we're going to do an example problem because that's the best way to learn, in my opinion, is lots of examples. But we'll just start with one for today. But I'll probably do a video with a few more in case you want to see them. And the one we're going to do is we're going to have f of x equals 2 to the x power, right? And what we're going to ask you for is the domain, right? The range, then we're going to ask for the end behaviors, and there's going to be 2 instances where you need end behavior. So it's going to be end behavior when as x, this line just means approaches infinity, we want to know what f of x or y is going to approach, right? And then we also want to know as x approaches negative infinity, what is happening to f of x or y. And I'm going to show you how that works, don't worry. The y-intercept and the asymptote. These are all of the pieces of information that you are going to need. And you can get them all off of the graph, right? Now, my graph does not need to be perfect, right? I'm just going to make it like this for right now, and we are going to talk about a few things. I'm just going to make an X and Y chart, right? You guys are going to be able to actually plug this into Desmos. You can actually just put the equation as you see it into Desmos when you do it and get the graph. I'm not asking you to know how to graph these. I just want you to understand the trends on the graph. So I'm actually going to have you plug them into Desmos just to get a sketch of the graph, right? You don't have to come up with all the points for it on your own. But when I'm graphing something, I always like some negative points, 0, and some positive points, right? That's always how I make a graph, because if I'm looking at a trend, I want to see what it's doing in the negative, I want to see what it's doing at 0, and I want to see what it's doing when it's positive, right? And if I plug these in to our equation, which was f of x equals 2 to the x power, when I plug in -2 here, this is just going to give me 1/4, right? If I plug in -1, I'm going to get negative, I'm sorry, not negative, I'm going to just get 1/2, right? We can look at that as 0.25 if we want. We can look at this as 0.5. 0, anytime you raise something to the 0 for 1,000,000 points, does anybody know what happens when you raise something to the power of 0? They're imaginary points, just so you know. You're not getting an actual 1,000,000 points. Heck, as long as it's imaginary, for 1,000,000 imaginary dollars, what happens when I raise something to the 0 power? Liliana, do you know? No? Anybody? All right. Anything raised to the power of 0 equals 1. If I raise this to the first power, I just get itself. If I raise it to the second power, I get 4. Notice there are no negatives anywhere in here. Good guess, Alfonso. There isn't a single negative anywhere in here. And the reason there isn't a single negative anywhere in here is no matter what I put in for x up here, I am never going to get a negative answer, right? No matter what gets put in for x, everything is going to stay positive. No matter how far I go in this direction, it's staying positive. No matter how far I stay in this direction, it's staying positive, which means that my asymptote, right, is the x-axis. This is never going to cross the x-axis. And when I graph this, it's going to look something like this. And like I said, this is just a trend. This is going to cross at 1 when x is 0, right? We know we have a point at 1. This is going to get closer and closer and closer and closer to this line, but it will never touch it, and it will never cross it, right? That is our asymptote. We could even write in right now, our asymptote is y equals 0, right? We will get infinitely close to that line, but we will never cross or touch that line, right? Because we can just keep making that fraction smaller and smaller and smaller and smaller and smaller, but it'll never actually be 0. So let's look at the things based on this. Everything we need is in this graph here to answer every question we've got. The first question is, well, what's our domain? Is there anything x can't be? We know that y can't be less than 0, but is there anything? Are we limited by any x? I think we can go forever in this direction, and we can go forever in that direction with our x's. So our x's, our domain, is all real numbers. So we could write it like this is the set of real numbers, or we could write it as negative infinity to infinity. Both things mean the same thing. Y, on the other hand, our range is our y values. And we know that we are limited on that, right? Because we can't go below this line. We can go up for infinity, but we can only go down to that x-axis, right? And we can't touch it and we can't cross it. So we can either say that y is greater than 0, or we can say that it goes from 0 with a parentheses, because it's not including 0, to infinity, right? These are two separate ways of writing the same thing. I don't care how you write it, as long as you're clear that we're going from 0 to infinity without actually including 0, right? This says y is greater than 0. It can't equal 0. This one's saying the same thing. By the parentheses, it means it can't actually equal 0. If it could equal 0, we would have a bracket. So end behavior is something that you haven't seen before, but it is not super difficult to look at or to figure out. It's saying as x approaches infinity. That's how you would read that. As x approaches is what that arrow means. Infinity. What's happening to y? What is y approaching? Right? F of x. So as we're getting bigger and bigger in this direction, what is happening to our y? Right? Is it going up or is it going down? It's going up, and it's going up forever and ever and ever and ever, right? So as x approaches infinity, as x gets bigger and bigger and bigger, f of x, or y, is also approaching infinity, right? It's also getting bigger and bigger and bigger. Now, if we switch that up, and as x approaches negative infinity, or as it moves in this direction, it's going down, but where does it stop going down? Right? Doesn't cross this line. So it stops going down where y equals 0, right? At that asymptote that it can't cross, right? So as x is approaching negative infinity, y is just approaching 0, right? It's not going to ever reach 0, but it's going to approach it. It can't cross the line and move into the negatives towards negative infinity. It can only go to this line. The last bit of information is the y-intercept. And the y-intercept's really easy if you remember that the y-intercept can be found by setting x equal to 0 and solving for y. But we have already done that, right? Because we set x equal to 0 and we got 1 for y. So we could say y equals 1. We can write the point 0, 1. We can just say that the y-intercept is 1, right? And it's where that point crosses the, right, this right here is our y-intercept. It's where the graph crosses that x-axis, right? So this is given to you in the graph, but all you have to do is remember when I said anytime you raise something to the 0 power, we get 1, right? So it should almost always be 1. These are all the pieces of information I need you to have for today. We could do several problems like that, right? But it's always going to kind of follow that pattern. You're going to look at the graph and have every piece of information you need based on this graph. And I'm not even asking you to come up with the graph on your own like I did with the table. I'm saying you can plug it into Desmos, right? And look at it. If I did that, let's see what that would look like. If we come over here and we go to Desmos graphing calculator, boom, I should have just had it open for you, especially since I'm recording this. But you can kind of plug in we can write it as y equals, what was it, 2 to the x power, right? And you get that same graph, right? Where are we crossing the y axis? 0, 1. Bam, that's our y-intercept, right? Are we ever crossing this x-axis right here? No, we're getting infinitely closer to it, but we're never going to touch it or cross it. Every piece of information you have is right there, right? Everything you need in the same respect. I drew the graph. You don't have to plot your own graph. You can just plug in the equation, right? Remember that you can write f of x as just y up here, right? And it's going to give you all of the information you need, your range. Bam, we can take any x we want. Y, everything above this line, right? Our range, everything above this line. What's happening behavior-wise is x gets bigger, y gets bigger, right? As x goes to infinity, y goes to infinity. As x goes to negative infinity, y just gets closer and closer to 0, right? So all of your information is in the graph. And I'm not even asking you to graph them when it comes time to do this. I'm just asking you to plug it into Desmos and see how the trends go on it. So for today, that's all I'm going to give you guys. So I'm going to end this recording because you've got that example.